Remember that. Oops, wrong one. So if I can now take this triangle, slide it on over here, I'm putting this base, this side, on this space. So from straight ahead, it would just look like one rectangle, but we know that the vertex is pointing out towards us, and we'd have small ones over here. We stack them on top of each other, and we smash them all in there, really, really tight, really, really small little bases, and that's why it's a continuous smooth curve. So like we talked about yesterday, the area of the equilateral triangle is here. The √3/4 side squared. We talked about how we definitely have a width. Right now, it's just the width of my marker. And since this is along the x-axis, the width of all of these are the change in x. That's why it then gives a volume, because we now have 3 dimensions. And then we don't just want one, we want all of them. So that's what the integral would do. So we've been pulling out the constants. We've been doing our integral. We want to come up with an expression for the side, because the side of all those equilateral triangles would be changing. And then the width, anytime we're vertical, would have to be measured along the x-axis. So that's our width. I don't know why I got a 2 right there. This is r, and then our 2 goes right there. So if we look at these sides, here's the side that we're trying to define, here, here, here. We look to see, since it's a vertical segment, is there something on top? Is there something on the bottom? And there pretty clearly is. So we do top minus bottom. The top is that curve, 2 root sine of x. The bottom is the x-axis, so 0. The limits are pretty straightforward. You were told to go from 0 to pi, so then we go from 0 to pi. All right. Then if you have a calculator in your hand, which you could do, keep in mind, maybe this is a nice one to review just to make sure we don't completely forget this, that we want to make sure we can do these without a calculator as well. So something like this, when we do these without a calculator, you want to clean up the integrand, the inside part, so square that. So that would just be 4 sine of x. So when we now go to evaluate these, the 4s end up canceling. And then if you remember how to do that, we just do the antiderivative of sine, which would be negative cosine. Put the negative out in front with the √3 from 0 to pi. This might be just as quick as plugging it into our calculator anyway. Cosine of pi would have been a -1, minus cosine of 0 is a +1. So we get a -2 on the inside, multiplied by the negative √3 on the outside. So this would have an area of 2 √3. If you use your calculator, not sure what that is, 3.4-ish. Okay, if we threw that into the calculator, this is irrational, so it's going to spit out that decimal value. All right. So that's what we did yesterday. Good little review there, I guess, because now 5 and 6 are the big ones. So for the first time, when we go to numbers 5 and then number 6a, you're going to see this phrase now, perpendicular to the y-axis. So we know the y-axis is vertical. So for the first time, we're going to be putting in our segments or our cross sections horizontally. So our curves are 2x and x squared. So y equals 2x is a line through the origin with a slope of 2. We're going to stay in the first quadrant, so we don't really need anything outside of it. And then x squared, again, we don't necessarily need this over here since we're first quadrant only. It would look like this. The area is here. Your cross sections that we're going to be putting in are semicircles. But we are going to do that so that when we put them in, they are perpendicular to the y-axis. So what we have been doing, we did a semicircle a couple of times yesterday. If I draw them in like this, like we did the other day, and we draw it in, that is not perpendicular to the y-axis. You're running parallel to the y-axis. So that's the phrase that tells us if we're vertical or horizontal. So for the first time, we're not vertical. Now we're going in horizontally. So now we got to think of a circle that gets cut in half. And the semicircle, then, this is the side that we're going to be laying on that space. So now it goes on here, perpendicular to the y-axis, perpendicular to your y-axis, and then just understand it doesn't go up the circle. If we had a 3-dimensional shape, it'd be out towards us. Same process. with the whole idea of our area, since it's a semicircle, you're going to have 1/2 pi r squared. So our volume then is the 1/2 pi, and then the sum, the integral. We need to define our radius for all of these, multiplied by our width. So the width is the key here in all of them. If I'm going to ask you how wide each of these semicircles are, so if I look at this one right here, wouldn't the width of this, if I could extend this, wouldn't the width of this be measured along the y-axis? That's how wide that pencil is horizontally. Same with this one. This one I made a little bit wider. This one here, our width is the change along the y-axis. So when we go to define this, our width now is going to be dy. Mentioned it a few times. I'm going to continue to mention it. If you can keep that straight, anything vertical has a width that would be defined along the change in x, or the x-axis. Anything that's horizontal, like number 5, your width is measured as the change along the y-axis. So because of that, this whole integral has to be expressed in terms of y. So when we go to set this up, when I go to try to define my radius, let me make this bigger. So I'm going to do this one right here. It's now a horizontal line segment. So instead of top and bottom, we've got to do right and left. So if I start to draw in my radius right here, and I want to do the right side minus the left side. Hopefully you can see that. That's pretty big. The right side is our parabola. The left side is nothing, correct? Because it's just out here in space. So it's another one like yesterday where if we're really going to do this, we want to define the diameter first. So I'm going to extend this all the way over, knowing that what I've really just done is define a diameter. And the diameter would be the parabola minus the line. And now here's where you need to be careful, because if we're doing this with respect to y, the way these equations are currently written are problematic. So we can't do the parabola as x squared minus the line as 2x. So if we were to define this as x squared minus 2x, we're not going to have this in terms of y. So when I don't know, I erase that. If I'm going to do the parabola minus the line, the way we're going to define that, the parabola, hope I can make this a little smaller now. I'd have to solve this real quick for x in terms of y. So that would initially give me the x equals a positive or negative root y. Since the x's that we're concerned about over here are on the positive x side, then that's the positive radical y. So that's how we're going to define our parabola, as root y. And then the same thing with our line. We don't want to define our line in terms of x. We need to solve that real quick for the x value in terms of y, and the line could be written as x equals y over 2. So knowing when to rewrite is pretty critical. It's the only thing sometimes that gets a little bit tricky with these, and if we can get that down pat, this usually goes pretty well. So when we now go to define our radius, the right-hand side was root y. The line was the left-hand side, but then keep in mind what we just defined down here was our diameter, so that we actually had curves to go between. So our radius would then be this cut in half. Now, before you plug it into the calculator, I would strongly suggest simplifying that a little bit. That's pretty ugly to plug in. We're not done quite yet setting it up, though. We still need our limits. Since I have change in y, I have y's here, I have y's here, you need to now make sure that your limits are written with respect to y. So they both go through the origin, so that's the same either way. Our lower limit is definitely still the y value of 0. And then this intersection point we need, but we need it in terms of the y coordinate. We want to know where do these intersect up here with respect to y. So now we're going to take those. You can do it in a couple different ways, I suppose, but whatever those intersections are, that's going to be your upper limit. All right. So if we set those equal, root y equals y over 2, square everything. I squared over 4. Yikes. Yeah, okay. myself some room. Why am I making this hard? It should be 4, right? X equals. Squared equals 2x. Yeah, so 2, and then our y's are 4. So we should get our upper limit there to be 4. All right. All right. Good with that. Makes sense, hopefully. All right. And you can throw that in the calculator. Honestly, I don't know what it is. I don't necessarily want to plug it in because I want to make sure we get to crank a bunch of these out. Because I want to do one more where it's perpendicular to the y-axis. This is actually an old free response question. There was a part C to this as well that we don't know how to do just yet. But this is an old question. Oh, no, that's the same question we just did. Shame. That's what happened. All right, that would save some time. Go to letter B. Go to letter B. See if we understand what this is asking. This threw some people off a little bit. So that same region we just dealt with, that's our graph. You have your cross sections. They're going to be perpendicular to the x-axis. You're going to put them in vertically. Instead of a geometric shape as a cross section, a circle, semicircle, square, or an equilateral triangle, they're giving you this as your cross sections. So see what you think there. And then this was a non-calculator question as well. That's actually why they didn't want them to evaluate this. So they would have expected you, once you have this integral set up, to solve this by hand. You would not have had a calculator in your possession for this question. That's why they gave you the graph, just so we know what those look like. So if you were confident in your setup, you could then go ahead and see if you can answer the question in its entirety. Although I don't know if I want to wait that long. So let's see if we have our setup done. So what's different about this? All the ones we've done so far have been either a circle, semicircle, a square, or an equilateral triangle. And all we've done to get this as a volume is we've assigned a width to all of them, because a cross section is always going to have a width. You can't have a cross section if it's entirely flat. So all we've done is taken our area equation. So here's the area, here's the area, here's the area, and we've multiplied it by a width. Just because it's not a geometry figure anymore doesn't mean that changes. We are now given the area right here. So if we give this a width, now we have a volume. So instead of us doing a geometric shape in here, they're basically, think of kind of a sine wave graph in between here. So now it's kind of like it's got some moguls in there, all right, some hills going from one curve to the next curve. So if we're going to set this up, all we want to do is always, pretty much every problem, are we really just taking our area equation and multiplying it by our width? Normally it's geometry shapes like over here. In this case, they're just telling us what that area is. It is the sine of pi over 2 x multiplied by our width. Since you were putting these in perpendicular to the x-axis, we're now back to being vertical. So our width would be the changes in x. Since we're going in terms of x, that area starts at 0 in terms of x. It finishes at 2 in terms of x. And then now let's see if we can actually solve this. So if I ask you to now evaluate that, we did one today. Let's do another. Antiderivative should be negative cosine. We leave that inside alone. And then if you remember, the antiderivative, we would divide by the coefficient of that x. So you divide by pi over 2. And then we evaluate that from 0 to 2. Dividing by pi over 2 is the same as multiplying by 2 over pi. So I'm going to pull that out along with the negative sign. And then we're just evaluating the cosine of pi over 2 times the upper limit minus the cosine of pi over 2 times your lower limit. Hopefully I have just enough room here. So what this upper limit, when we plug that in, what that really evaluates to be is these 2's cancel, is the cosine of pi. So -1. Actually, second time we did this. The next one is the cosine of 0, which is a +1. So -2 over pi on the outside, -2 on the inside. So that answer should have been 4 over pi. All right. The AP test used to be 3 calculator and 3 non-calculator questions, and these used to always be calculator. But as the calculators have gotten more powerful, they've had a hard time doing it. So now these are almost always non-calculator. That's why they give you the curve, just so you don't mess that part up. You can't even get it going. But a lot of these have become non-calculator over the last handful of years. Okay, so be able to handle that. Antiderivative, upper limit, lower limit, all that stuff we did prior to this section. Okay, so with that, what should be on the next page, instead of what we just got done doing, we called it volumes. So we're still dealing with a volume here in 7 point. This really is going to be like what you did last year in your Math 3 classes as you rotated things, because these are now volumes of a solid of, here's the word. So when you did all of these with Mr. Quillos, and he's judging how good of an artist you are with all of that, you're going to do all that again now. All right. And we do this 3 different ways. The first way is what we call discs. All right. So the disc method, it says if we are given a curve and told to find the area underneath that curve, you are dealing in 2 dimensions, the x-axis, upper limits, so on and so forth. If we were to take that graph and rotate it around the x-axis, then that's going to give our area a depth, and as a result, we could then be dealing with 3 dimensions, allowing us to find the volume of that figure. So what I want you to do, sketch in the equation y equals x. I'm going to change this just for something that I'm going to show you here on the computer. Make this 0 to 8, just so it matches sort of the online tool I'm going to show you here in a minute. So just graph y equals x. So it just goes through the origin, a slope of 1, and say we're going to stop over here at 8. So this is our space. What I'm telling you to now do is take that, basically that blue triangle, rotate it around the x-axis. So this is fixed. So think of the x-axis as a fixed, like a gate almost. Here's our post, and we're going to rotate that thing around the x-axis. So if I'm going to do a rotation, we should, in 2 dimensions, basically, it should be symmetric to the x-axis. And what should be happening as we rotate this, we should be kind of creating this circular idea. So if we understand that, can we see how that's kind of like a solid cone? All right. So what this is saying now, when anything is revolved, some kind of a circular shape is formed, we know how to find the area of a circle. So what I want you to do next is to draw a circular disc in the figure. Actually, what I want you to do next, this all revolves around the idea, when we first started all these areas, that we have these rectangles in here. So draw a really tiny little rectangle in here. Visualize what would happen if that rectangle rotates around the x-axis. Wouldn't this one rectangle, if it rotates and its fixed point is right here on the x-axis, if that rotates around the x-axis, can we kind of see how that would form a disc? If not, this is what I have, that this hopefully is very clear. If it works, it was just working. Of course, now it's not. We may have to come back to it. But think about if on ours, we'll see if it ever stops. Sure, wait. If that thing gets rotated around the x-axis, then hopefully we understand that it reappears down here, and as it's doing that, it basically is creating this solid circular disc. It's like a wheel, a thin old wheel, wooden wheel, getting rotated around the x-axis. Well, we don't just have that one, right? We would have another rectangle over here. That guy gets rotated around the x-axis, creating his own circle / width. We would have bigger rectangles over here getting rotated around the x-axis, so on and so forth. And if we keep putting the next one and the next one and the next one, then it ends up being this solid continuous shape. All right, can we kind of see that? It doesn't look like my internet visual is going to work. So that's what I wanted you to do here. Draw a circular disc in that figure. This figure then has an area of pi r squared. That's the flat if it was flat. What we would need to know is what is the radius of our circles. All right, and then the volume can be found by multiplying the area by the width of our disc. So the same exact idea that we were dealing with our cross sections. So let me do it all up here where we can see it. You can kind of follow the words. So the area of each one of those discs, if we were just talking its surface area, on one side would be pi r squared. But each one of them has a width. So whatever the width of our rectangles would be, or our circles would be, each one of them has a volume. Okay. I'm going to try one more time, see if it came back to me. Nope, still spinning. So what we're going to do in order to get the volume of that entire shape is add all of these circles with their width. So basically the disc. So when we go to now set this up, similar to the cross sections, I would pull the pi out. What we now need to figure out is what is the radius of all of those circles in there, all those circular discs. For sure, these have different radii, right? Here's for me anyway, this is the one with the biggest radius for my drawings. This one's in the middle. Here's my smallest circle. But if I were to ask you to define the radius of any of those, notice how they're all vertical radiuses, radii. So we're back to doing a top minus a bottom. So if I wanted you to define this radius right here, we just look, what's on the top of that radius? And it would be this equation, y equals x. And then the bottom of that radius would be the x-axis, which is 0. If I did the same thing over here, if I did this radius, isn't x also on top of that radius? 0 is on the bottom, same with this one. So no matter where you drew your circle, x is always on top, 0 is always on the bottom. That's how we could define any radius within that region. The width of all of those, since my rectangle, if I go back to drawing one original rectangle in here, wouldn't the width of all of these now be whatever the width is along the x-axis? So that's our dx, and our limits for this one would be 0 to 8. So all we're really doing, the integral acts as a sum. It's going to add up. It's going to calculate the limit of us throwing more and more of those in there, and all we're really doing is pi r squared multiplied by the width, and that's why it is a volume. Okay? And then that's really easy to plug into the calculator, so we don't necessarily need to practice that. But that's the disc method. Number one, I was just asking you to kind of show that one, so we've already done number one. So skip ahead to number two. We'll do another one. Ah, there it is. It showed up. Hopefully we're kind of understanding it anyway. Let me get rid of the discs. Maybe it's not. It's still spinning. Anyway, without me being able to slide and show you all this stuff that we have on here, I did it in 4 rectangles. Oh, there we go. And if I were to rotate those around, those 4 rectangles get rotated around. And as it rotates around, it would fill itself in. Each one of those then creates the discs as we rotate around. We would generally start this idea with a Riemann sum. We would want the width of all of those, but eventually we want to calculate more and more and more of those in there. So if I start throwing more and more in, the function changed on me too, so I went back to the default. The more and more I draw in there, and see how this now smooths out, and we get this smooth, continuous, solid shape. All right. And that's what the integral will calculate for us. What limit do we start to approach? What volume do we approach? We put more and more rectangles and discs in there. All right. All right, so with that, wrong page, let's go to number 2, because this is that one anyway. Here's the root x curve. So go ahead and draw root x, and we'll tell you to stop at 4. That's our area. We're going to rotate that around the x-axis. So if I were to take this region and I rotate it around the x-axis, it would reappear down here. As I did it, what we're kind of creating now is a kind of a bullet-looking shape, an acorn who's missing his hat, but it's solid the whole way. All right, that's our graph. And then this all revolves around what we started all this area off with. So draw in one of those rectangles. So just draw in one rectangle. Think about how that would produce a circle, a circular disc, if we rotated that around the x-axis. So as this rotates around the x-axis, it's going to create a circle. And then we have all of these. You don't have to draw too many if you're understanding, but all of these together smashed in there gives us that smooth, continuous shape. So what we need to do is add all of them up. That's what the integral does for us. It adds them all up. What we are adding together is basically circles that have an infinitely small width to them. So we do pi r squared, and then that really tiny width is defined as the dx. Since we're in terms of x, the limits are quite easy because you're going 0 to 4. We can just look at our graph. And then no matter where I draw mine, no matter where you draw yours, if I draw in the radius for this one, and this one, every single one of these, the radius is bordered on top by that radical curve, and then on the bottom by the x-axis, which is 0. Okay. And then that's it. That one's probably just as easy to do by hand as it would be to pull out your calculator. You know, if we just did not x squared, sorry, that would have canceled. So square that radical. So this would just give you x squared over 2 from 0 to pi. Not 0 to pi, 0 to 4. So we would get what? Pi times 8 minus a 0. So our answer would be 8 pi. All right, 3. Root x again. So draw in the root x. Let me not do it too far along. So draw in the square root of x again. We're still going to go to x equals 4. But instead of the x-axis this time, I want you to use y equals 1. This is why I mentioned, I don't know if I mentioned it to you guys, probably did. Vertical and horizontal lines, critically important. We don't screw those up. You might laugh and say, I would never do that. People mess those up all the time. This y equals 1 is a horizontal line through 1. So here's 1. You don't really need to extend it over here. Just worry about the area that we're going to be dealing with over here. So y equals 1 comes through here. So the area that's now enclosed by those two curves, and x equals 4. X equals 4 is this vertical line. So we kind of already have that. Oh, no, we didn't. I just jumped the gun a little bit. I was a little too excited. So then the vertical line x equals 4 is why we stop at the 4. So the area we're talking about now that we're going to rotate is this. We don't always go around the x-axis. So for this one now, what I'm telling you, you're going to rotate this around the line y equals 1. So we're actually going to rotate it around this horizontal line that's bounding us on the bottom. So if we did that, this point right here is where our reflection would begin. It would reappear down here. Looks similar to number 2. It's just now kind of a thinner and sleeker bullet. I would still strongly recommend drawing in these discs or starting with your rectangle. So draw in one of our rectangles that we're going to rotate. As that gets rotated around the x-axis, the line y equals 1. Do another one here. As that gets rotated, we start creating all of these circles. By circles, I mean discs, circles with a width in them. See if we can set this up. See if we're understanding. because it's similar to that previous one, but you should have a couple of things that are a little bit different now. All right, so the simple part is it's a sum. The integral is finding that infinite sum of circles, so pi r squared. Since these are vertical circles, our width of all the rectangles that we would have been drawing in there would be our change along the x-axis. So when I now go to define my radius, I kept one of them drawn in here. If I draw this one in, you're just looking to see what's on the top of both of these, what's on the bottom of both of these. So the radical, that root x, is still on top. But what should now be on the bottom of any radius would have been a 1, the horizontal line 1. We definitely go to 4 still. We would have continued to draw in circle upon circle upon circle till we get to this very last one at the end. But our first ones would not have started at 0 now. Our first circles would have started to get drawn in right here. And that would have been the intersection of the root x curve and 1. So maybe you don't have to set those equal to each other, but in general, that's how we can find that. Square both sides. Your lower limit needed to be a 1. All right, did we get that at home? Good. All right, so that's that. So now we go to number 1. But if you look here, horizontal discs. So if you notice, these are all vertical discs. As we rotate around a horizontal axis, that rotation is going to create vertical discs. So if we now go down to this one, number 1, be able to draw this on your calculator with a short of time here. We don't necessarily have the time to do it on our calculator, but this is back to the whole second draw inverse, so you know what these look like. So just make sure we are capable of doing that. X over 2y, you would get something down here. We don't need that because I'm going to ask you for y equals 1, between 1 and 4. So the part we need is the part of the graph that would be up here. So this is what this graph looks like. So this is the x over 2y. We only want the y values from 1 to 4 and then the y-axis. So if I did 1 here and then 4 right here, we now have kind of this bound on the bottom at y equals 1, and we have our upper bound up here at 4. So this is our region here. This time, however, I want you to rotate it around a vertical axis. So now I want you to rotate this around the y-axis. So if we're going to spin this around the y-axis, now this, in terms of 2 dimensions, the reflection should occur over here in the second quadrant, kind of like this. So that's 2 dimensions. But think if we're rotating that now in this direction, think about that kind of circular motion. We're no longer, if we're going horizontal, we're not creating circles going up and down. We're creating circles going sideways. So the circular motion that we are now creating through that rotation is creating horizontal circles. The reason that's important is because it's the same method, right? It's still circles that have a width to them, and we want to add them all up. So we're still going to be doing pi, the sum of all of these, our radius squared. But when we now go to define our width right here, if we're horizontal, if I actually drew in a rectangle, I suppose I didn't. If we would have drawn in a horizontal rectangle, wouldn't our rectangle's width be getting measured along the y-axis now? So the width of all of those circles would be the change in y. That means all of this now has to be defined in terms of y. Since our circles are horizontal, that means every radius is going to be horizontal. So that means now we're to the rights and lefts. So let's do this one here. If I look what's on the right of this radius, it would be the curve. What's on the left of the radius would be 0. Same for this one. Curves on the right, y-axis on the left, same here. So we're going to do the curve, 2 over y, minus the y-axis, which is 0. Our limits have to be y values, so make sure that we have those. In this case, pretty straightforward. Our biggest circle would have started at the y value down here at 1, and we continue to stack them until we get to the very top up there at 4. So we should be going from 1 to 4. Kind of looks like a volcano when I'm doing it on the computer, black and red. All right, or a tree stump. And then again, whatever the C-value is, this we could do by hand. You can throw it into your calculator. These are pretty reasonable to do by hand if we want it. Okay. All right. Well, we might actually. No, we won't. Just kidding. Let's jump to 3. 2 and 3 are identical, except I want you to, in this one, the y-axis, rotate it around the y-axis. We're going to use x equals a negative 1. 3 is the harder of the two. So I'd rather do that one. And then you could probably go back to the first one and be fine. So x equals 1 minus y squared. If you can't do this without a calculator, know how to do the second draw inverse. And then x equals a negative 1 vertical line at x equals a negative 1. So that this is our region here. You're going to rotate that around x equals a negative 1. So it should kind of look like this. This is our y-axis. This is x. This is x equals negative 1. That rotation around a vertical axis, if you think, now this is kind of like a gate almost, like if you think is that axis of rotation here, the x equals a negative 1, that stays the same, and we swing it around that vertical post, you're going to be creating a bunch of circular motion in a horizontal direction. All right. Those are pretty bad there, but oh well. Oops, wrong way. Okay, so let's set this up real quick. Go ahead and set that up. We got a few minutes. See if we can set one of these up. We're inside 2 minutes here, so let's make sure we get this done without rushing too much. If I ask for the radius of any of these, so if I draw the radius into this circle, or that circle, all of them would have been bordered on the left by that parabola, 1 minus y squared. Every one of these radii would have been bordered on the left by that horizontal or vertical line, negative 1. So we do the parabola minus the vertical line. Since we're horizontal, the width of all of these, now that we're horizontal, would be the change measured along the y-axis. Our limits have to be y's, so just make sure of that. It's easy to think maybe we're finishing over here at 1 because we know that's a 1, but that's in terms of x. So our limit should be from right here, whatever this y value is, to right here, whatever that y value is. So that would require a little bit of work. You would need to set those two equations equal to each other, figure out where they're equal. So we get what? Y squared equals 2. So we should get positive and negative root 2. So this would have been a negative root 2. This is positive root 2. So then those end up being your limits. All right. Okay, kind of got through that. I didn't necessarily think that was going to happen. Reminder, I am going to make a video, 8th period today. I'll have it hopefully up by 3:30 between now and Monday. At time of class, you will want to have watched that because we're going to go right to the next set of notes. If you understood this, you're going to find that video to be very, very nice, and most people don't find this terribly difficult. The next one is very, very similar to what we just did. I think you'll be fine just watching the video, okay? All right, so I'll get that posted. Have a good weekend. We'll see you guys all on Monday.